Okay, so I've fixed the, well, some of the mistakes on the notes and figures, okay? So usually the notes should be, and usually the class should be ready at least an hour before the class, but usually my classes are ready after the class. So I always tend to be extremely late. Because then I realize what is wrong and what is missing, and then I fix it. So the notes are usually good to read after the class, which is good, right? So I'm fixing and adding things all the time. So I fixed this figure that Johnny showed me. So I was showing the zonal wind stress, meridional wind stress was supposed to be curl and divergence, but when I did the plot, I didn't do the curl and divergence, so I just replotted the zonal component of the wind stress. But it said curl and divergence, but it was just the zonal wind stress. So I will fix that.
Professor, I'm sorry. If you could share the screen, otherwise in Zoom we can't see the slides. Thank you.
Sorry, they said they could see it.
Oh, they can from Zoom?
Saverio e Andrea, potete vedere quello che faccio vedere sul...
No, vedevo solo la lavagna.
Vedete solo la
lavagna.
Ah, ok.
Allora no, deve fare share screen.
Ok.
Ok.
Adesso sì, grazie.
Sorry. Okay, so ladies are ready. So we were saying that the ocean is forced and is heated and cooled at the surface, contrary to the atmosphere, and so it's forced by momentum fluxes, zonal and meridional components of the wind stress, and that's a climatological map of the zonal and meridional wind stress components. Okay, you can see clearly strong zonal components of the wind stress in the regions of the Antarctic circumpolar current. Okay, that's why it's one of the largest currents in the ocean. And you can see band of positive and negative. And what we said is that, what we mentioned, and we will explain why, we mentioned that the ocean is driven by wind stress, but not exactly the wind stress, but the wind stress curl. Okay, and so whenever you see the zonal wind stress changing sign, that will be eventually this afternoon there will be a plot of the curl. Okay, and so the curl is what drives the ocean, and we will explain why is it the curl and not the wind stress per se. Okay. Today, I think today we will mention briefly why you need the curl, but then we will demonstrate. Okay, and then there's not only momentum fluxes, but there's also buoyancy fluxes at the surface of the ocean, of course. Okay, these are the components of the surface fluxes: net short wave, net long wave, latent heat, and sensible heat. Okay, you can look at the details. You can see where the ocean is losing heat and the ocean is gaining heat. We can go into the details later. And precipitation and evaporation fluxes at the surface. If you put together all the heat flux components and P minus C, in the ocean we say E minus P, in the atmosphere they say P minus C. Okay? What you get is the buoyancy fluxes at the surface, which is the net heat flux and the net freshwater flux at the surface. Okay? So a lot of heat gained in the equatorial regions and in the southern part of the southern hemisphere. Heat loss in the regions of those western boundary currents that we mentioned, okay, the Gulf Stream and the Kuroshio. Why is the ocean losing heat? Because it's relatively warm temperatures of the ocean relative to the atmosphere. And there is a net heat flux out of the ocean. Again, if you come from an atmospheric course or an atmospheric background, usually signs are switched in the ocean. Okay? Heat upwards in the ocean is negative because the ocean is losing. In the atmosphere is the other way around. N minus P is the same thing. More precipitation in the equatorial regions, subtropical regions of net evaporation, and more precipitated where you have the subtropical atmospheric winds. Okay, so this is how the ocean is forced at the surface. You can have fun looking at the details. Basically, momentum and buoyancy fluxes at the surface, and that will determine the ocean circulation. Okay, as I was saying the last time, the ocean is not forced. Each ocean basin is not forced the same way because of geographical differences. Okay, if you look at heat flux, for example, okay, clearly from the colors. If you look at the heat fluxes in the Atlantic, in the North Atlantic, and the heat fluxes in the North Pacific, you see that they're very different, okay? And that's mainly because of the extent of the Atlantic Ocean reaching farther north than the Pacific. And the E minus P fluxes, the freshwater fluxes, you can't really see the colors here, but they're also different. Okay? So the buoyancy flux that the North Atlantic receives, one of the reasons is that it reaches far north, is different from the Pacific, and that makes the surface North Atlantic properties different from the properties of the North Pacific. Okay, the North Atlantic is saltier than the North Pacific. The North Atlantic is cooler than the North Pacific. That makes the water denser in the North Atlantic, and that makes the North Atlantic surface water sink to a certain depth and generate a deep circulation, whereas that doesn't happen in the North Pacific because of the different surface forces. And because you have formation of deep waters, as we said the last time, so from the surface properties you can look at the interior properties, and you can see differences in the Atlantic. You see a signature of North Atlantic deep water being produced and Antarctic bottom water being produced in the southern hemisphere, whereas you can't really see that in the Pacific, okay? Because the Pacific is not producing deep waters in the north, okay? And you cannot see that. So that's why the circulation in the Atlantic Ocean is very different from the circulation in the Pacific Ocean. Right? It's one of the reasons. The surface forcing is very different. So some people might say that whatever happens in the ocean is due to the atmosphere. Okay? So, however, the atmosphere forces the ocean and the ocean responds. And because of geographical differences and the presence of continents, then every ocean basin develops a different dynamics. The main ingredients are the same. Okay? We will see, for example, the development of the wind-driven gyres. They are forced by the same dynamical reasons in each and every basin. But then the response is different, especially in the case of buoyancy forcing at the surface, developing this deep circulation. Okay, so we said that these tropical gyres, these arrows, they are mainly forced by the same mechanism, wind stress curl, okay, and you see the gyres everywhere, different shapes because of different continents, but the theory is the same. But this is not true for the deep meridional veterinary circulation. So the vertical convective cells in the ocean are different in the Atlantic and in the Pacific. This is the case for the Atlantic, where you form North Atlantic deep water and you form Antarctic bottom water. And this North Atlantic deep water is eventually upwelled in the southern hemisphere through Necron Pumping that we will see on Friday. And this doesn't happen in the Pacific. So if you put everything together, then you get this picture that we saw the last time. You have the deep water production in the Atlantic. You don't have the deep water production in the Pacific or in the Indian because of different buoyancy forces. But you have upwelling everywhere in the southern hemisphere because of this Ekman upwelling, driven by those large zonal component of wind stress that we showed before. That large zonal wind stress component flowing westward. With a westward wind, again in the ocean we say that a wind that, we said the opposite, so the westward current means, what do you say, in the atmosphere you say where the wind is going, in the ocean we say where the current is coming from. So it's westward, so it goes in this direction. And that drives an Ekman flux and an Ekman upwelling. We will see all that. Okay? So that happens everywhere. But in the Atlantic is the only place where you have this deep water production. Okay. And then you have upwelling of deeper layers in the Pacific and in the Indian Ocean, closing this meridional returning circulation. This is a simplification, of course, but it gives you the main pathways of the surface and deep branches of this meridional returning circulation. If you look at a model, as I was saying, so I had a terrible plot, now I have a slightly better one. If you look at the meridional returning circulation in a model, so you take the velocities, you compute a stream function, and then you plot the stream function for the global ocean. So you zonally integrate over the global ocean, or you just take the Atlantic Ocean, or you just take the Indian Pacific Ocean together, and you compute the meridional returning circulation through, and you visualize it through the stream function. Then you see this different circulations. So the top is the global circulation, and you see again the familiar North Atlantic cell, okay, then crossing all the way to the southern hemisphere. There's very little vertical mixing upwelling water. Most of the water goes crosses the equator, goes all the way to the southern hemisphere, and then upwells in the regions of the Drake Passage, so between Antarctica and South America. And then you see this Antarctic bottom water production, okay, this negative cell, blue is negative transport, okay? And this is relatively small compared to observation, because I was saying models tend to produce too little Antarctic bottom water because of the problems that we mentioned. Okay, so this is the global meridional returning circulation. If you just look at the Atlantic, you see that this cell is basically the same, because all the North Atlantic water is produced in the North Atlantic. Okay. And if you look at the Indian and Pacific Ocean together, and you compute the volume transport, you see that there is no deep water circulation. There's very little deep water circulation. You're supposed to see a little bit of Antarctic bottom water here. I guess the colors, the contours of the colors are not high enough to see it, but there is a little. Okay? There is a little of Antarctic bottom water and intermediate waters going into the Indian and Pacific and then being upwelled by vertical mixing. But you don't see any deep circulations because of the different buoyancy forces at the surface. Okay. What you see are these subtropical cells that are wind driven by the surface wind stress in the equatorial regions that you see in the Atlantic, of course. Okay? So very different circulation depending on where you are. So what we're going to do is first restate a little bit some basic assumptions that you've seen in GFD and maybe in the first part of this course. And then slowly build the theory of the wind-driven gyres and the wind-driven circulation. Okay, so I will give today a couple of tools that we will use. Okay, and then on Friday we will talk again about Ekman layers in terms of the ocean upper Ekman layers, which is what is going to connect the wind stress, the momentum flux, to the interior of the ocean, and that will be used to explain the wind-driven gyres. And when we talk about Ekman frictional layers, we also talk about the vertical velocity induced by the Ekman fluxes. And that Ekman velocity will be important for explaining the upwelling of these waters, okay, the Ekman pumping, and the Ekman pumping in the center of the wind-driven gyres. And then after we introduce that, or we revisited that, we will start with the theories of the wind-driven gyres that will connect the momentum flux of the surface, the curl, the Ekman layer, with the Ekman pumping associated with it. And that Ekman pumping will transfer momentum to the upper layer of the ocean, generating the wind-driven gyres. And then at the end we will go back to the buoyancy-forced meridional returning circulation. Okay, so I just put here in case you want to revisit what we saw in GFD, some of the things that we will use. Okay, the Lagrangian derivatives, streamlines and string functions. So you have everything in one document. The divergence theorem, the Stokes theorem. And now we'll start with what we're going to use today. Which are things that you've seen already, but let's talk about it again. So first, hydrostatic balance. Okay? I'm going to write it down because I will use it to explain geostrophic currents, thermal winds, and all that. So hydrostatic balance. Okay. So I'm not going to start again by writing down all the momentum equations, but you should know by heart your momentum equation by now. Okay. So the vertical component of the momentum equation is just dw by dt. Okay, the Lagrangian derivative, and that is equal to d by dz of the pressure minus the gravitational force. Okay, that is your vertical component of the momentum equation. So W is the vertical component of the velocity and G is the gravitational force. So if you're in static, and you remember what static is, the gravitational terms is balanced by the pressure gradient. Okay, this is 0. And so we have dP by dz equal minus G rho. Okay? And this is your hydrostatic balance that you're probably sick of seeing. Okay, and this is a good approximation for large-scale motions in the ocean, especially where the horizontal scale is much larger than the vertical scale, so that U is much larger than W. Okay? So the horizontal velocities are much larger than the vertical velocities, so you can make this approximation and use the hydrostatic balance, which is actually what is used in most ocean models, atmospheric models, climate models. Most have the hydrostatic balance approximation. So you can show that the hydrostatic balance is nothing but a small scale aspect ratio, okay? Meaning that the horizontal velocities are much larger than the vertical velocities, or that the horizontal scale of the motion is much larger than the vertical scale of the motion. And this is true for the atmosphere and the ocean. Okay. So if you start from the momentum equation, in a bosoneous fluid, I'm going to use this notation. Phi is going to be P over rho naught. And then I'm going to use buoyancy minus G rho over rho naught. Okay. And then the vertical component is buoyancy. Okay. I like to use buoyancy. So if F is equal to 0, okay, you can make the approximation. If F is equal to 0, then this goes away. And so you can start making a scale analysis of your momentum equation. And so scale analysis for the horizontal component is nothing but U over T, okay, this one, which scales as phi over L, okay, this term. Or you can write this L over T, or this can be written as Lu over T, that scales as phi. Or U squared scales as phi. Okay? And we're going to use this later. Okay, so this is a scale analysis for the horizontal component. Now you can use mass conservation, okay, to scale the vertical velocities. The mass conservation horizontal operator. So if you make scaling for this is U over L plus W over H equals 0. Or UW is HL H over L U. Okay? And you can call this H over L as alpha. And so alpha is going to be our aspect ratio, H over L. So a typical horizontal scale over a typical length scale. Sorry, typical H over L. Yes. Okay, so this was using the mass conservation, so now let's see the effective vertical component. So this is W, so typical vertical velocity over some typical time. This is U over L W. And this is U over L, the W is this one, H over L U. Okay. And this is U square over L square H. Okay, so this will be the scaling for the convective term in the vertical momentum component. Not making any mistakes, I think so. Okay, so now we can use both. So for the hydrostatic balance to hold, then this has to be much smaller than this, right? That's what we said. That in hydrostatic balance, the gravitational term, what was it? The pressure gradient balances the gravitational term because this is very small, okay? So this has to be much smaller than this one. So this over d by dz has to be much smaller than 1. Okay? This is the necessary condition for hydrostatic balance. And now you can use the scalings, which are this, okay? U square over L square H. That is over d by dz of phi. That was square over H. Where is it? Oh, phi U squared, yes. U squared over H. Okay. So we use this one and this one. This has to be, which is we get H squared. Okay. If you get rid of everything else, and that has to be much smaller than 1. Okay, so we just started. We just did the scale analysis for the horizontal component of the momentum equation. We used mass conservation to get this scaling, and then we looked at the advective term or the vertical component, which is this, and this is the condition for necessary condition for hydrostasy. Okay. The advective component in the vertical the advective term in the vertical component has to be much smaller than the pressure gradient. And if you use the scale, you get to this. But we know that this is alpha squared. Okay, so alpha squared has to be much smaller than 1. So hydrostatic approximation, or the hydrostatic balance, is nothing but a small scale aspect ratio approximation, which is what we intuitively knew when we neglected some of the terms, but you can prove that it's just an approximation, a small scale aspect ratio approximation given by this. Okay, so that's one of the main things that we will use, of course, hydrostatic balance, which is nothing but small scale aspect ratio approximation of the horizontal flow being much larger than the vertical flow, and the horizontal scales being much larger than the vertical scales. And that will determine the theory that we will use and the result. Okay, so I will leave that. Then something else that you might have seen and you might have heard about is the Rossby number. Okay. So the ocean, as the atmosphere, is a rotating stratified fluid, okay, and is affected by rotation. How do you know if your flow is affected by rotation and if rotation is important and has to be retained in your equation? It's basically given by the Rossby number. Okay, so if you take again the horizontal momentum equations, right, that V is UVW and U is UV0. Okay, so if you make a scale analysis again of the second and third term, okay, you have U square over L, and then you have FU. Okay. Typical velocity, typical length scale, typical velocity, and F, the Coriolis parameter. So if you make a ratio between the advective term and the rotational term, you get the Rossby number, which is U over FL. Okay, so if this is small, so smaller than 1, then rotation is important. Okay? Rotation is important, so has similar, so the term is larger than the advective term, and so the Coriolis term, the acceleration, the rotational effects will be important and will shape your dynamics. Okay? Everything is in the notes anyway. So now we can remember what a geostrophic balance is and thermal wind. We use the term thermal wind in the ocean because it's just taken from atmospheric dynamics. So it's the same principle. Okay, so if the Rossby number is sufficiently small, and then your dynamic is affected by rotation, so rotation dominates over the nonlinear advective terms that we just saw previously. Okay? And so your rotation term F is going to be much more important than the nonlinear advective terms. And if you remember, you also have the d by dt. So if that term also scales advectively, so has the same size of the advective term, then the Coriolis term, the rotation term, dominates over the advective term and the time-dependent term. And so the only thing that remains in your momentum equation, that I'm not going to write again, but is the geostrophic balance. Okay. So if Rossby number is sufficiently small, dominates over the advective scales, over the advective term, and if the d by dt, so the time-dependent term, scales advectively or is 0, then the rotational term also dominates over that one. And so those two terms cancel out. And what you're left with is the Coriolis term balancing the pressure gradient on the other side. So you have dp by dx and fu y. Okay, these are the only terms that are retained in your momentum equation. And so the rotation term balances the pressure gradient. Okay? And this is true for Rossby number sufficiently small. Okay? So that the rotational term dominates over the advective term and the time-dependent term. And this is your geostrophic balance that you probably remember. Yes.
Is both SV. Isn't the second one supposed to be SV?
Yeah, my handwriting is terrible. Okay, and so this is your geostrophic balance, and you can define your geostrophic velocities, of course. Okay, so you can use U and G. You can say that this is your geostrophic velocity, and this is your zonal component of the geostrophic velocity. So what is the geostrophic velocity meaning, which is a very good approximation in the atmosphere and in the ocean, is that your geostrophic flow will go parallel to lines of constant pressure, okay, because this part is balancing the pressure gradient. And so, if, for example, you have this case, a low pressure or high pressure in the ocean or in the atmosphere, in the northern hemisphere, around the low pressure, you will develop an anti-clockwise circulation because the flow starts to go down the pressure gradient, and then Coriolis kicks in and it deviates it to the right in the northern hemisphere, and then eventually there is a balance between the pressure gradient towards the low pressure and Coriolis. Okay? So there's a balance between these two terms. And eventually the flow in geostrophic balance, frictionless flow, will go around the low pressure in this sense and clockwise around the high pressure. And this is a good approximation in the ocean. You know, every time we see a map of surface pressure from satellite, for example, you can infer from the pressure gradient on the surface the geostrophic velocities in the ocean, same as in the atmosphere. What you can do when you, for example, make this plot and you compute a stream function, okay, is define a stream function. You can define a stream function for your geostrophic flow as well. Okay. You can take a horizontal flow so that your conservation of mass is this. This is your continuity for a horizontal flow where W is equal to 0. And you can define a function such that u is minus Vy and v is d by dx of c. Okay, you can define this function, and that satisfies continuity. And this is going to be, because I've used this before, so I'm going to write, not to use this, not to use the same thing. And so this is going to be your stream function. Okay, and so if you go back to the geostrophic balance that we just showed, and you use your continuity for a geostrophic flow, that's vg dx plus vg dy, and this is equal to 0. Okay, that's my continuity. You can define the geostrophic stream function. Okay, what I showed you before is not the geostrophic stream function, it's just the total stream function, is not just the geostrophic component. But you can define for a geostrophic flow your geostrophic stream function and plot your streamlines and stream function. Okay. Which is what we normally do once we compute our velocity field. Okay. Sometimes we plot the velocity field, sometimes we plot the stream function in order to compute volume and mass constants. So these are all the different streamlines in this total stream function computed from the total velocity field. Okay. But you can do the same for a geostrophic flow. Okay, so this is your geostrophic balance. And through geostrophic balance, you can obtain the thermal wind equations. And the thermal wind equations are useful in the ocean because it's basically telling you what the geostrophic field is going to be in the interior of the ocean given a horizontal gradient in buoyancy, temperature, or salinity. Okay, so if you have a horizontal gradient in temperature, for example, that will determine a geostrophic flow in the interior of the ocean, just like in the atmosphere. So am I using the same? Okay, so if I use my geostrophic equations for a Boussinesq fluid, and I take the vertical derivative, okay, just taking the vertical derivative of the Boussinesq fluid, and I combine this with the hydrostatic balance. Okay, so I'm going to substitute the hydrostatic balance into this geostrophic flow. So I've used the geostrophic balance, and now I'm using the hydrostatic balance to replace this d by dz of p in here. So I change the order of differentiation, and I get to dz of u is g dy of p rho f z du. Rho. Sorry, I'm substituting this rho. Okay. So I took the geostrophic balance, then I used the hydrostatic balance to replace this, change the order of differentiation in pressure, and I get to this. And this is the thermal weight balance. Okay. So it's nothing but taking the geostrophic flow and using the hydrostatic balance to get to the thermal weight. So what is this telling us physically? It's telling us that a meridional gradient in density, could be temperature, okay, determines a interior geostrophic flow that has a vertical component. Okay. So the vertical derivative of this geostrophic flow will be given by the horizontal gradient in density. So as long as you have a horizontal gradient in density or temperature, then you will develop a geostrophic flow with a shear. So for example, so what I'm saying here is what I just said. So you have a geostrophic velocity, fine, and that's given by the geostrophic balance when the Rossby number is sufficiently small and the pressure gradient is balanced by Coriolis. But if you have a horizontal gradient in density or temperature, for example at the surface, then you will have a shear in your geostrophic velocity. Okay? And that vertical shear is called the thermal weight, just like in the atmosphere. So for example, take a very idealized case in the ocean. Okay. Zone average temperature, neglecting salinity, just take temperature for a stably stratified fluid. So don't think about the North Atlantic deep water formation where you're not stratified. In a stratified fluid, density increases with depth. Okay, obviously. And so if you take a zonal average, so for example those plots that I was showing you of temperature and salinity zonally integrated, okay? Just think of a zonal average of the ocean interior. So d by dx of rho is equal to 0, and you're left with this. Okay, you're left with this component. So we're interested in the meridional gradients of density, neglect salinity, meridional gradient in temperature. That will generate what? That will generate a geostrophic flow, a zonal component, that has a vertical shear. Okay, so as in the ocean and the atmosphere, if the temperature falls in the polar direction, so poles are colder than the equator, of course, okay? So temperature is cooler at the poles, so this meridional gradient of density is larger than 0. And so if this is positive, then the geostrophic velocity will also be positive, and so eastward, like in that case. Okay. So you will have, so if this is the pole and this is the equator for the northern hemisphere, this is denser, so colder, and for a stably stratified fluid, this is also denser than the upper layers. Okay, and so this meridional gradient in temperature will generate a zonal geostrophic velocity that has a vertical shear, and the wind shear increases as you move upward in the ocean. And so this d by dz of u is larger than 0, and so it will be a current that is surface intensified, so it's larger at the surface, and then slowly decreases towards the depth. Okay, and this is a very useful. This is a very useful, it's crude approximation, but it's very useful, like in the atmosphere, to compute geostrophic velocities in the ocean. If maybe I have a map, I should put a map here. I will put a map. No. Well, imagination, I will add them up. But with a bit of imagination, look at the Atlantic Ocean in the southern hemisphere. In the southern hemisphere, what you have is this. Okay. Row 1, row 2, row 3. Okay. Row 3 is larger than row 1. So it's denser, so it's colder at the pole. We are in the southern hemisphere, so F is negative. Okay. And so if you have the stratification, so you can go into the ocean and measure stratification. Okay? You cannot measure velocity everywhere, but you can measure stratification in a few points and get stratification in the ocean or density. Okay? So if you have this map, then you can compute the thermal wind in the ocean or the geostrophic velocities. So where is the geostrophic velocity directed in this case? So we are here, rho F d by dz of u g dy rho. Is this positive or negative? This is negative, and this is
negative, so you just the derivative of u with respect to z is positive, so towards the east.
so this is positive, still out of the boat. Okay, and that's the Antarctic circumpolar current that is flowing out of the screen. Okay, so what is happening in the ocean is that you have the strong wind stress at the surface, okay, driving from west to east. Okay. All this positive zonal wind stress flowing at the surface of the Southern Ocean, so out of the boat. It's very strong. What it's going to do is going to cause vertical Necron pumping that we will see on Friday, and that will tilt the isopycnals, the lines of constant density. Okay? So you start in an ocean at rest. You start with parallel stratified ocean, row 1, row 2. Then you start heating, you start blowing the wind stress over the surface of the ocean. And the surface of the ocean will cause an Necron flux that we will see, that is directed in this case, and that will rise and tilt the isopycnals. Okay? So once you rise and tilt the isopycnals, then there is a surface Necron velocity that we will see on Friday, but we don't care about that. The interior of the ocean will respond by this tilting of isopycnals by generating a geostrophic flow. And this geostrophic flow has a shear. So it's larger at the surface and it's getting smaller and smaller as you go deeper at depth. Okay? And so the ACC, the strength of the Antarctic circumpolar current, can be computed by the thermal wind relation. Okay? And so what you do, you actually need, once you integrate this to get the values of the geostrophic velocity, you need the value at some depth of the geostrophic velocity, and then you integrate your equation. So you need to get a measurement or get a level of no motion. So you assume geostrophic velocity to be 0 here, and that is going to be your level of no motion. Did you do the geostrophic balance calculation with the with Miro? Yes. Okay. And then you compute you integrate, and you get your geostrophic velocity. And this is how you measure actually the Antarctic circumpolar current. I mean, people cannot measure geostrophic velocity everywhere and all the time. So what they do is they compute the stratification, and once you get, well, you measure stratification, that's easier at some point, a couple of points. Once you get the stratification through thermal wind relation, you get the structure of your geostrophic flow. But this is the baroclinic part. Okay? Then you have a baroclinic part, and then you have a barotropic part, which is independent of the vertical. and that requires a different measurement. But this is the baroclinic component of the geostrophic velocity. So baroclinic meaning that it depends on the on density or on the vertical. Okay. Okay, easy. So we looked at the remember hydrostatic balance. We remember the hydrostatic balance, Rossby number, geostrophic balance, thermal wind, and now the Rossby radius. Okay, and why we care about the Rossby radius. Okay, so the Rossby radius of deformation is very important in the ocean as well as in the atmosphere. It sets basically the size of every large-scale dynamics that you study in the ocean and in the atmosphere. Okay. It's a fundamental length scale for both the ocean and the atmosphere. What it does, it describes the horizontal scale at which rotation becomes as important as buoyancy. Okay? So if you are smaller than the Rossby radius, rotation doesn't affect or affect very slightly your movement, your dynamics. If you are comparable to the size of the Rossby radius, then your phenomena will be affected by rotation. Okay? And you can do, and this is you can do for a geostrophic flow. You can do an adjustment problem. Okay, so basically, imagine you take the surface of the ocean at rest. You make a disturbance, like a wind burst over the surface of the ocean, and then you generate a height anomaly. Okay, like above. So at the beginning, the disturbance is small, and so gravitational effects dominate over rotation, and rotation is not important. Then the disturbance starts to become larger and larger. Okay, starts to spread over a larger length scale, and then once it's spreading, then rotation becomes important when it reaches a certain size, and that size is the size of the Rossby radius. Okay, and so once the disturbance has reached the Rossby radius of the formation for that particular latitude, then rotation becomes important and determines, and then you are in geostrophic balance. Then rotation balances the pressure gradient. Okay. And so you can make that geostrophic adjustment problem by taking the potential vorticity conservation, having a disturbance of the surface, and it's very easy to show that the Rossby radius of deformation is nothing but the phase speed of the gravity wave. So imagine that this is the initial disturbance, okay, and this is eta, and then after some time, this disturbance has spread over a certain length scale, and this length scale is the Rossby radius of deformation. And once this disturbance has spread over this length scale, now rotation is becoming important. And now you are in geostrophic balance, and Coriolis balances the pressure gradient. Okay. And so the Rossby radius of deformation can be shown very easily to be the ratio between the gravity wave phase speed and the Coriolis parameter f. Okay. H over f. Okay. This is for a homogeneous case. Okay. This is very large. If you take numbers for a typical depth of the ocean of 4 kilometers, the barotropic gravity wave phase speed is 200 meters per second. The Rossby radius is 2,000 kilometers. Okay, it's huge. So you might think that you never get 60,000 kilometers, okay, before frictional effect and everything else kicks in. But actually what we care in ocean dynamics and in the atmosphere is not the barotropic Raspberry radius of deformation, but the baroclinic Raspberry radius of deformation. Okay? The ocean is not just rotating with F, but is also highly stratified. So what we really care about is the baroclinic Raspberry radius of deformation, where you take into account not the barotropic gravity wave phase speed, but the baroclinic modes of the gravity wave phase speed. Okay, and so usually you take the first baroclinic Raspberry radius of deformation, which is C1 over F. Okay, and now the first baroclinic gravity wave phase speed is 1.3 meter per second. Okay. F is 10 to the minus 4, and that gives you a Raspberry radius of deformation in the ocean of about 10 to 30 kilometers. Okay. That's much smaller than in the atmosphere. The atmosphere is almost an order of magnitude larger, and I will tell you in a second why that's important. Okay, so the first baroclinic radius of deformation is about 10 to 30 kilometers, depending on the latitude. Okay, so C1 varies, but especially F varies with latitude. Okay. So the baroclinic Raspberry radius of deformation depends very heavily on latitude, and it goes from 10 to 30 kilometers. So it's very small. So that's the typical length scale of your dynamics that is in geostrophic balance. So dynamical features in the ocean, like in the atmosphere, tend to organize themselves around the length scale of the Raspberry radius of deformation. So in the atmosphere you see big cyclones and anticyclones. They have a certain shape and size, which is huge, because the Raspberry radius of deformation in the atmosphere is huge. And so you reach in a cyclone and anticyclone geostrophic balance, Coriolis balancing pressure gradient at that large scale, and that's why you form cyclones and anticyclones. In the ocean, the Raspberry radius of deformation is very small, and so in the ocean you tend to form the equivalent of cyclones and anticyclones at that scale, and those are called mesoscaletes in the ocean. Okay, those circular patterns similar to cyclones and anticyclones that go around the ocean, and they are much smaller, 10 to 30 kilometers. And then we will see when we look at wind-driven gyres, the theories of the gyres, that is also the shape of the western boundary current. The shape of the western boundary currents, they have a scale, a width, that scales as the Raspberry radius of deformation. Okay? And so that's much smaller than in the atmosphere. And I will tell you in a second why. But anyway, so the Raspberry radius of deformation in the ocean, extremely important to understand ocean dynamics and how oceanic features they tend to organize themselves. And so what you do, you take the first baroclinic Raspberry radius of deformation, which is given by first gravity wave phase speed and F. You can compute from observations the gravity wave phase speed. Okay. That's given in a stratified ocean. The reality is given by stratification. Okay, N is the Brun-Weisala frequency. So you should know what it is. You can actually compute, do a normal mode decomposition, the gravity wave phase speed. Okay, N equal 1. That's the first mode, and that's just a vertical integral of the stratification in the ocean. That gives you the phase speed of the gravity waves in the ocean. And so what you need is just temperature and salinity from observations. You can compute stratification globally. Then you vertically integrate, and you get the gravity wave phase speed in the ocean. And this is what you get in reality. Okay, on the left, you get the baroclinic gravity wave phase speed from observations. Okay, so red is large and blue is very, very weak phase speeds. Okay, depends on the stratification. So where you don't have much stratification, gravity wave phase speed is very small. Where you don't have strong stratification, where you convect and you form deep waters or bottom waters around the Southern Ocean and the North Atlantic. Okay? There, N stratification is very weak, it's very small, and so the gravity wave phase speed is also going to be, the baroclinic gravity wave phase speed is also going to be very small. Otherwise, difficult to see on this projector, but you get, wherever you have stronger stratification, you have larger gravity wave phase speeds. Okay. And this is a zonal mean of C1. And this is the same computed from a Kleiner model. It's similar, but it's different, and that's because the model has biases in the representation of the temperature and salinity structure, therefore stratification. And so it's a good representation of reality, but it's not exactly matching it. But anyway, you take C, you can put C from observations or a model, and once you have C, then you just need to divide that by F, and you get the Rossby radius of the formation, which is, how do I know? Okay, now this is the first baroclinic Rossby radius of deformation. So simply C1 over F. Okay, and this is the zonal mean. Again, from observations and from a Kleiner model. First thing that you see clearly, C1 varies in space, but what strongly sets the baroclinic Rossby radius of deformation is F. Okay, it's very large at the equator. Actually, here at the equator, you have to compute the Rossby radius, not through this formula, but for the equatorial Rossby radius of deformation, because geostrophic balance doesn't hold there. And that's why I didn't do it in the Kleiner model. But in the observations, I did. So the Rossby radius is very large at the equator and is very small towards the pole because of F. Okay? So this means that in equatorial and subtropical regions, the Rossby radius is around, let's say, 100 kilometers. So dynamics, shapes in the ocean will be on the order of 100 kilometers. And dynamics and big features in the ocean in subtropical latitudes will be on the order of 10 to 30 kilometers. Okay? So relatively small. So that's why if you see a map of mesoscaletes in the ocean, you will see large mesoscaletes in the equatorial regions, and the same feature is going to be very small as you approach subtropical and subpolar regions, because the Rossby radius is much smaller. So you obtain Geostrophic balance in a much shorter distance. And this is for our Kleiner model, which is not bad. Okay. Similar, but not the same. Now, I was mentioning this also because, as I said, in the ocean, Rossby radius is much more than the atmosphere. Okay, so that means that whatever is larger than the Rossby radius, whatever is smaller than the Rossby radius is not in geostrophic balance. And this is a map, this is a very nice map that shows you what is the oceanic resolution in an ocean model needed to resolve the Rossby radius of deformation in the model. Okay? So remember that the Rossby radius is highly dependent on latitude because of F. So how much resolution do I need to resolve the Rossby radius in the equatorial regions? It's about 100 kilometers. So I just need a 1 degree ocean model. A 1 degree cell roughly covers the Rossby radius. But the Rossby radius is about 10, 20 kilometers at this latitude or even smaller. So what do I need to resolve the Rossby radius? What kind of resolution? I need something about 1/16 or over 125 degree here to resolve the Rossby radius. Okay? This is not doable in a climate model. Okay, it doesn't happen. I work with a 1/4 degree ocean model. There are climate-ish simulations with 1/10 or 1/12. Okay, otherwise it's too expensive. But usually, real climate simulations, my experiments are done with 1/4 degree, maximum 1/8 or 1/10. So ocean models are not resolving the Rossby radius of deformation poleward of 50 degrees or 60 degrees. That means that whatever you cannot resolve with the ocean model, you have to parameterize it. Okay, and so that's something that in the atmosphere you don't have to worry that much because the Rossby radius is much smaller. And so with a coarser grid, you can resolve the Rossby radius in the atmosphere almost everywhere. Okay. So there are features smaller than the scale of the Rossby radius that you don't need to parameterize in the atmosphere because you're always resolving the Rossby radius, whereas in the ocean you're not. Okay. So many sub-mesoscale dynamics in the ocean are not resolved in the ocean and have to be parameterized. Whereas in the atmosphere, it's easier to have a horizontal resolution that resolves the Rossby radius everywhere. Okay. And so to give you some eye candy of what it means in an ocean model to resolve and not resolve the Rossby radius, this is the same coupled ocean-atmosphere model. In one case, the ocean has a 1 degree grid. In the second case, it has a 1/4 degree oceanic grid. In the third case, has a 1/12 oceanic grid. Okay? The atmosphere is the same. And this is just a snapshot of horizontal velocities, I think. 1.2, yeah, it's probably velocity. So this is what you resolve with a 1 degree ocean, which most people use, and most climate models use in those IPCC assessments and CMIP runs and projections for the future. Many climate models still use a horizontal resolution in the ocean of 1 degree. This is what the horizontal surface circulation looks like. Okay? You don't see any circular patterns, filaments, eddies being resolved there. Okay? The general structure is probably good. Temperature and salinity in the interior are probably okay. The strength of the gas stream is probably fine. The strength of the meridional returning circulation that I showed before has been tuned to be okay. But you're not resolving mesoscale eddies. You're not resolving everything that happens in the mesoscale eddies and smaller than that. That has huge vertical velocities associated. That sets also the large scale dynamics. So that is totally missing here. When you use a 1/4 degree ocean, things start to appear. Okay? You start to see filaments here in the northern side of the ACC. You start to see eddies being resolved by the ocean model. And when you go to a 1/12 degree ocean model, then you see a very nice Gulf Stream. The eddies detaching from the Gulf Stream, so you resolve the instabilities. You see all these different features in the Antarctic circumpolar current, which is very turbulent and it has a lot of eddies. Okay, which is totally missing here in this 1 degree ocean. Okay. This is a problem that atmospheric modelers don't have. Usually the resolution in the atmosphere is good enough to resolve cyclones, anticyclones, and things like that. Okay. So this is what we used to do, and some people still do. This is what we're doing now, and this is what people do for very short simulations because it's too expensive. Okay. But actually, if you're interested in ocean heat uptake, so anthropogenic heat uptake, or uptake of CO2, then that uptake of CO2, for example, happens a lot in the Southern Ocean, happens a lot within mesoscale eddies where you have strong vertical velocities, where you exchange heat and fluxes with the atmosphere. So if you're not resolving that, you are missing a large part of of the ocean dynamics. So that's why the Raspberry radius of deformation is important. Okay. So now let's finish with the other concept that I want to introduce, which is the beta plane. I don't know if you have looked at the beta plane before, but I'd like to show why the beta plane is important and where it comes from. Okay, so the ocean is rotating. Okay, we saw the geostrophic balance, the thermal wind, and how rotation affects the structure of ocean dynamics in terms of the Raspberry radius of deformation. But sometimes when you want to develop your theories and you want to use your equations, doing that with spherical coordinates can be cumbersome. Okay? So, and not useful for elucidating the main mechanism. So what you want to do is work with a Cartesian plane, but retain the spherical properties of your dynamics. Okay, you don't want to get rid of the sphericity of the Earth because that sets much of the dynamics, meaning that the Coriolis parameter depends on latitude. Okay? And so you don't want to get rid of the dependence of latitude, but you don't want to use spherical coordinates because sometimes can be not necessary. And so well, you can make an approximation, and this approximation is called the beta plane. Okay? And so you do the beta plane to retain your sphericity, but working on a Cartesian plane. Okay? So I'm going to try to draw this. Okay, so this is my rotational vector, and this is my sector of the Earth. Let's say not a hemisphere, yes. Let's say not a hemisphere, F is positive. Okay. I don't want to use spherical coordinates, but I want to work on a plane that is tangent to the sphere. This is going to be my height, z equals 0, of my plane, and this is going to be my y, x into the board, and z of my plane. Okay, so I want to go from the spherical Earth to this plane that is tangent to the sphere. Okay, this is going to be my latitude theta naught, and this is going to be my latitude theta, and this point is going to be a theta minus theta naught. This is a, the radius of the Earth, and I think I'm done with drawing. Okay, so this is my plane at z equals 0. Okay, this is tangent to the sphere, and this is going to be my beta plane. And it's tangent on the sphere at a latitude naught and longitude naught. Okay, longitude or x into the board. Now for small variations in latitude, so theta naught and theta have to be the difference between theta naught and theta have to be small. For small variations in latitude, I can approximate the tangent of theta minus theta naught to theta minus theta naught. Okay. And so my coordinates in this Cartesian plane are going to be y, a theta minus theta naught with this approximation. It's supposed to be tan of theta minus theta naught, but I can make that approximation for small variations in latitude. Then my x is going to be r minus I minus a. So r is the distance of the fluid from the center of the sphere, okay, and a is the radius of the Earth. So let's see. Okay. And then x, what used to be the longitude, is going to be phi minus phi naught a cosine of theta naught. Okay. You can easily work out this. Okay, so what I wanted to do is go from my spherical coordinate to this Cartesian plane that is tangent to the sphere. Okay. So now I have my new vertical coordinate z, which is r minus a. A is the radius of the Earth. Then I have y, that for small variations in latitude is just a theta minus theta naught. And x is phi minus phi naught, the longitude, times a cosine of theta. Okay, so I went from a theta phi, the spherical coordinates, to x, y, and z. Okay, this is useful because now I have a linear relationship between theta, the latitude in the spherical coordinates, and my new y. Okay, so now my theta is theta naught plus y over a. Yes. Okay. Yes. So again, for small variations in latitude, what is sine of theta? Sine of theta is sine of theta naught plus the cosine of theta naught y over a. Okay. If you make a series, truncating the series on theta naught. Okay. Again, for small variations in latitude, sine theta is sine theta naught plus cosine of theta naught y over a. Okay, so this is my new Cartesian plane that I call the beta plane. And I call it the beta plane because now I can write my f, my Coriolis parameter, that used to be 2 omega. Theta, right? So it used to be 2 omega sine of theta. But what is sine of theta in the beta plane for small variations of theta is 2 omega sine of theta naught plus y over a cosine of theta naught. is 2 omega sine of theta naught plus y over a sorry, 2 omega is missing here. 2 omega cosine of theta naught y over a cosine of theta naught. But if you substitute the y over a, this is 2 omega sine of theta naught plus 2 omega over a cosine of theta naught y. Theta naught. Okay. 2 omega sine of theta naught, 2 omega over a cosine of theta naught y. Yes. Okay? So my f is now 2 omega sine of theta naught, and I will call that f naught. So the Coriolis parameter at some latitude theta naught, where my beta plane is centered, plus, I will call this beta y. Okay? So I'm using a beta plane so that I can go from f 2 omega sine of theta to f naught, because the beta plane is centered around the latitude theta naught, plus beta y. Okay, so the sphericity is returned because I have beta, and beta is the meridional gradient of f. But I work on a Cartesian plane. I work with y. I don't work with theta. Okay, so it's much simpler. So this is my beta plane, okay? Perhaps you have seen beta plane before, saying instead of using f, 2 omega sine of theta, we're going to use the beta plane, which is f naught plus some variations in latitude of, because beta is df over y, okay? But this is how you get the beta plane. And so this is important because now we can use the Cartesian plane in our momentum equation and derive our theories for the wind-driven gyres. But you could say, okay, I don't care about the sphericity of the Earth, so I make beta equals 0, so f doesn't vary with latitude. And so I work on the f plane, and the f plane is when making f as a constant. So you work with f as f naught. Okay. But then f doesn't vary with latitude, and if f doesn't vary with latitude, you don't have propagation of features. For example, Rossby waves, okay, they propagate because there is a meridional gradient in f. That's their restoring mechanism. It's not gravity, like gravity waves, but the restoring mechanism for Rossby waves is the meridional gradient of f. So if you don't have a meridional gradient in Coriolis, you don't develop Rossby waves. If you don't develop Rossby waves, you don't have adjustment of large-scale features in the ocean, in the atmosphere. So this is good for working over very small length scales, or for looking at tropical cyclones, for example, very idealized tropical cyclones. But if you want to develop a theory for the large-scale subtropical gyres, as we will see, you need beta. Okay, you need the variations of f over latitude. Otherwise, you cannot explain the wind-driven gyres. Okay? But with the beta plane, you can have a much simpler set of equations. Now, if you want to see This is my very nice schematics. Okay, took me hours to do it, but I think it looks okay. And so this is how F varies with latitude. Okay, and this is how beta varies with latitude. It's just the meridional gradient over F. And it's something that you need. Okay, so if you give me 5 more minutes, I want to show you why you need beta and why you need to study Ekman dynamics. Okay? You don't have to go anywhere. No. Okay. So why you need beta and why beta is so important in setting up the large scale ocean circulation. So let's consider that Coriolis parameter is a function of latitude, of course, and we're going to use the beta plane. So F is a function of y, okay? It's a function of the meridional coordinate in our beta plane, in our tangent plane on the sphere. So you can use, again, a two-dimensional flow. So you have continuity, and continuity is telling you that the flow is no divergent. Okay, my two-dimensional flow is no divergent. And now, if you take your geostrophic equations, I don't want to make a mistake. Okay, you take your geostrophic equations Fu minus 1 over rho dp dy and Fv 1 over rho dp dx. Okay, so you are in geostrophic balance. You have a two-dimensional flow which is non-divergent. Now you cross-differentiate this horizontal momentum equation. Okay, df over x u plus f dx of u minus 1 over rho. Okay, cross-differentiate the first one. You differentiate the second one, df over y v plus f dy v over rho. Okay, cross-differentiating the geostrophic momentum equation. This is 0, d by dx of f. This we want. Okay, we don't work on the f plane, we want to work on the beta plane. This we want. So if you sum these two, you get d by dy of f v plus f dy v plus dx u equals 0. Okay, and this is beta, and this, how did I write it? Okay, remember that V, U, V, W, and U is U, V, 0. Okay? Now, if I use continuity, I go from this to beta V. This is minus d by dz the W. So fine. And this is a statement of conservation of potential vorticity. Okay? And what it's telling you, okay? And so how do you generate a vertical velocity? You can generate a vertical velocity through surface forcing. For example, wind stress, Ekman pumping, you generate a vertical velocity. Okay? And by generating a vertical velocity, what you do, the interior of the ocean responds by creating a meridional geostrophic current that depends on the meridional variations in F. So if you have, we will see this, if you have a subtropical gyre, Atlantic, Pacific, doesn't matter, okay, this is just a squared ocean, and you have a wind stress curl, not just a wind stress, but you have a wind stress curl in the northern hemisphere. Now you have a Ekman pumping into the ocean, okay, because the curl is into the ocean, and that generates a vertical velocity in the ocean, a downward vertical velocity. And the response of the interior of the ocean will be by generating a meridional velocity that depends on beta. This is going to be a negative velocity, vertical velocity is negative, so V is going to be negative. So the ocean interior will move to the south, okay, depending on the meridional gradient of F. If F was set to a constant, this would be 0, okay, and you wouldn't generate a geostrophic velocity. So that's why you need the gradient of F. And this is something that is called Westward balance. So next time we will see how you, from a wind stress and the wind stress curl, you generate an Ekman layer, you generate an Ekman spiral, an Ekman transport, but most importantly for large-scale ocean dynamics, you generate an Ekman pumping. This is WE. Okay, you generate an Ekman pumping through Ekman dynamics. And this Ekman pumping will set up in motion the interior of the ocean as a geostrophic current. And you need beta. And you need the variations of F in latitude. Okay? And again, this is just a statement of conservation of potential vorticity. You have an input of vorticity by the wind stress curl, and that input of vorticity by the wind is balanced by a variations in planetary vorticity. Okay? F, you know this, right? Planetary vorticity, relative vorticity, you've seen this. So F is planetary vorticity, and so the input of vorticity by the wind is balanced by a change in planetary vorticity. And why there's a change? Because there's a meridional geostrophic velocity. So as the flow moves meridionally, changes F. And so input of vorticity by the wind balanced by a change in planetary vorticity. So the flow, you can think of conservation of potential vorticity instead of geostrophic currents, that if you have an input of vorticity in the ocean column is forced to move meridionally in order to conserve potential vorticity. So if you have this, which is your potential vorticity, and this has to be conserved, if you have an input of relative vorticity, then the column of water has to move meridionally in order to conserve potential vorticity. And by moving meridionally, you create a meridional geostrophic current. Okay. That's why you need beta. Okay? I'll stop here. I'll work on the notes. Everything is clear. You never stop me like, I don't understand this, this is wrong. Now that we can have interaction, I'm disappointed. I'll put a plot here to show what this means. Okay, so I'll see you on Friday. Hopefully I'll see you on Friday. And I'll put this afternoon I'll put the notes on Slack. I wouldn't print them because I keep changing them again and again. So just look at the slides on your computer. Just don't print it. Okay. Tutto a posto voi?
Thank you.
Bye.
On Friday.
Ciao ciao. It's much better to be in class, right? Good. At least you move a little bit. See you Friday.
Ciao.
Bye.